Let's move on to item I, which is Tank 8 and Cathodic Protection System Review Projects. And that's Austin Love with Bill Mott. Go ahead, Austin.
Thanks, Robert, and good afternoon, everybody. For those of you who don't know, I'm a project manager with the council, and I'm helping coordinate this Tank 8 inspection and review project we have going. For this item, we're not asking for board action. The goal of today's presentation is for Mr. Bill Mott to educate the board and Alyeska and other stakeholders about what we're finding regarding the maintenance of crude oil tank 8 from the terminal. And the presentation that Bill's going to give is focused on what we found so far. And the plan is to have another presentation to the board in May to discuss recommendations and solutions that could help improve the maintenance of this storage tank, as well as other tanks at the VMT as well at the Valdez Marine Terminal. And before Bill gets started, Bill Mott gets started, just so some background for Bill. He's the co-owner of Taku Engineering based in Anchorage there. And he's a licensed engineer with the state of Alaska. And he's been doing planning and executing tank maintenance for over 20 years. And Taku Engineering, his firm, they provide engineering support for crude oil piping operators and tank farm operators throughout Alaska. And more specifically, Bill and Taku actually provided Alyeska and TAPS with engineering support for their system-wide tank program from 2001 to 2014. So Bill and his team at Taku are very familiar with the tankage along TAPS and the terminal. So with that, I'll let Bill take it away from here.
Well, thanks for the introduction, Austin. I appreciate it. And I appreciate the opportunity to be here. As Austin said, I want to talk a little bit about our preliminary findings on this project. Our primary goal for the study was to reduce the risk of damage to the VMT crude tanks that could result in either a spill or injury to personnel. We intend to accomplish this by reviewing the monitoring, inspection, and maintenance practices that have been undertaken with that tank. This is a photo of Tank 8. It was originally constructed in 1976. It's 250-foot diameter, holds a half million barrels of crude oil. The tank floor and a cathodic protection system were installed. A new tank floor and a cathodic protection system were installed in 1995. The tank was removed from service in 2007 and 19 for ensuing inspections. In 2019, minor repairs were completed. The tank was prepped for coating and returned service. Alyeska internally noted some inconsistencies in the inspection, and they initiated a follow-on inspection that identified more significant damage and prompted a plan to replace floor. Unfortunately, COVID showed up, and the floor replacement was delayed until 2023. Just give you a background on the API 653 inspections that are done. API is American Petroleum Institute. The standard 653 defines inspection repair processes that have been developed to reduce the risk of a spill or a leak from an above ground storage tank, an AST. API recommends annual visual inspections, 5-year in-service inspection, and then periodic out-of-service inspections. For the purpose of this study, we're referencing the out-of-service inspections. To conduct these, the out-of-service inspections, the tank's got to be removed from service, drained, vented, and cleaned. The inspection visually assesses, the columns, tank shell, a tank roof, and the tank floor, as well as the nozzles and some of the appurtenances on the tank. The NDE of the tank floor garners most of the attention. It's where most of the leaks occur. When I say NDE, that's non-destructive examination. Alyeska's floor plate inspections include mag flux exclusion, which it looks like an upright vacuum cleaner that runs around the tank. It alarms when it sees areas of thinning. They mark that out. They come back. They scan the area with ultrasonic testing, which gives them a direct measurement of the remaining thickness. Floor plates are typically repaired with a overlay patch they lay down and weld, seal weld onto the floor. I'm going to zoom in. I'm going to, look at one little spot in this to talk about it for a few seconds. This represents one small area of the floor plate. The original floor plate was 250 mils thick, or a 1/4 inch. The top side of the floor plate is coated. So we don't typically see any kind of corrosion activity on the tank side, on the liquid side of the tank floors. The bottom side is in contact with soil, and that's where most of the corrosion occurs. The second API inspection that Alyeska conducted, they repaired the floor to a minimum of 180 mils remaining. So this might be what a typical remaining pit in the tank looks like. It's got 180 mils of steel left out of 250. The code, the standard requires that the owner plan to have at least 100 mils of floor plate remaining at the end of the next service interval. So Alyeska started with that, and they had 80 mils remaining to get them through to 2023. That's 4 years from when the inspection was done in 2019. So Alyeska's corrosion calculations assume that the floor plate would experience 20 mils a year corrosion for the ensuing service interval. The reality, the actual corrosion rate on that tank has been closer to 10 or 11 mils per year. So I would expect that when they take it out of service, they're going to have somewhere in the neighborhood of 135 or 140 mils remaining on that floor. If you follow that little dotted line, that's probably what this pit would look like, but that's about what I would expect them to find when they go back in there. So I think as long as the data was collected in a prudent manner, and everything I've seen on the second inspection suggests that it was, I think there's very little risk of a corrosion leak on that tank before it's taken back out of service in 2023. One thing I didn't see, API 653 reports typically address tank settlement. There should be some perimeter assessments done on settlement, as well as internal localized settlement assessment on the floor. Especially in light of the November 2018 earthquake, I would have expected that to take a little higher profile. They may have conducted it, it just wasn't in their 653 report. This is a simplified cross-section of what a crude oil tank looks like, one of Alyeska's. Again, it's 250 feet across. The tank shell and the tank floor plate around the perimeter rests on a concrete foundation, a ring wall. There's no seal between the plate and the wall. There's about a 3.5 foot drop between the top of the ring wall and the bottom of the sump. So that plate slopes down to the top of the sump, and then the sump itself is 2 feet deep. So you end up with, it's actually 3 feet 7 inches. So next couple slides, I'm going to focus on this area right here. This is supposed to represent what that area looks like, where the tank shell rests on the annual plate. It's welded to the annual plate here, floor plate extension or annual plate extension, and that rests on a concrete ring wall. The ring wall was existing. There's no bond between the plate and the concrete. So any water that pools on that will either slide off the side of the ring wall, or it will migrate to seep beneath the tank in between the secondary containment and the floor plate. Most operators try to avoid that, and they install a flexible membrane, not a membrane, but a flexible grout to seal that area. So not unlike what you would put around your bathroom tub or around your windows at home. Alyeska, in fact, had a seal like that when they installed the tanks, but that hasn't been maintained over the years. So I apologize for the quality of the picture. We've asked for updated ones and haven't received them yet, but this is from I grabbed this from the 2007 out of service inspection. What you can see is the grout and the seal is cracked all around the full perimeter of the tank. Certainly in this picture, likely around the full perimeter. I don't believe any maintenance has been done on these since the 80s. If you take a cross section of that, it would look something like this. And the problem here is that water running down the tank is then almost funneled into the area underneath the tank. it exacerbates the amount of moisture that is seeping into that area. And why that's a concern is, as you recall, there's a secondary containment liner beneath that. If the secondary containment liner is intact, then the soils between the floor plate and the secondary containment become saturated with water. Valdez gets 70 inches of rainwater a year. That tank is over an acre of steel up top, and all that water collects and runs down the shell of the tank. Even if only 5% of that water seeps underneath the tank, these soils will be saturated in a year and a half. We're putting these back in service for 10 to 20 years. So for a majority of the time that they're in service, some level that the water impacting that sump is saturated. Now, Alyeska has installed subfloor drainage systems on these tanks in this area I'm pointing to right now. On some of the tanks, we don't know if they've done it on all of them, but that subfloor drainage is at this level. It's still significantly higher than the level of the tank sump. So while it alleviates some of the buoyant forces on the sump, it won't entirely alleviate it. We actually did get a call from somebody working with Alyeska that they had some distortions on the tank column feet when they went into the tank. We've requested drawing or photos of the as-found condition of that, haven't received them yet, but we've seen that before. We've seen the sumps float. We were told at the time it was groundwater intrusion, but for that to happen, you wouldn't have competent secondary containment. So I apologize. I have my dog with me because it's cold out today. So if you hear something in the background, it's Coda. So yeah, if you've got competent secondary containment, there's no way for the groundwater to ingress into that area. If you have competent secondary containment, the water that seeps in there from the unsealed floor plate extension has nowhere to go either. So this is a view that Alyeska provided of the tank 8 sump. You can see there are 4 columns in close proximity to that sump. The sump is 21 feet in diameter, so that'd give you a gauge of just how close those column feet are. This isn't clear enough for us to, we can only see one of the column feet, and we can't get close enough. We can't get it clear enough to determine if there's any damage there. And we really can't see the other 3. But that's what we'd be looking for, and that's where we've actually seen these column feet bent and distorted, and the floor plates somewhat bent up when a sump is floated. There are doubler plates underneath the column pads, which helps to reduce the risk somewhat, but the risk is still inherent in there. Next thing I'd like to talk about is cathodic protection. Most of you are actually probably familiar with that. They use them on boats all the time. These are zincs for the back of a boat, and it's bolted to the boat, so it's probably an aluminum or steel boat, and these are probably zinc anodes, and they provide a current that keeps the bottom of the boat from corroding. Well, tanks use the same exact science. Some operators are able to install perimeter anodes like this that drive current up to the tank bottom, and they can protect the tank bottom in that manner. Alyeska's got a secondary containment liner beneath that floor, which effectively blocks the distribution of current. So what they've had to do is to install anodes in this space between the secondary containment and the floor. It looks something like this. Alyeska's installed grid systems, which is mixed metal oxide ribbon that runs beneath the floor. It's connected with conductor bars, and then they actually run conductor cable back to a rectifier and provide current, which protects the floor from corrosion. Photo on the right is actually one of the Alyeska, probably tank 110 or 11 tanks, so one of the tanks up north. You can see they have girder columns instead of pipe columns like Alyeska. But you can see running, they leveled it out. They've got the ribbon run out. They don't have the conductor bars or the conductors installed yet. CP surveys on the tanker, they monitor these systems through a series of tubes, monitoring tubes that they run above this between the grid and the floor, and slotted so that they can collect voltages on the floor. And that's what they use to determine if the tank is in fact protected. So Alyeska and most operators worldwide follow criteria laid out by the National Association of Corrosion Engineers, or NACE. The two predominant criteria that are used are an IR-free potential or an instant-off potential of 850 or 100 millivolts of polarization. Please bear with me. I know this is probably a little more technical than you'll want, but it's to get the point across, so I have to kind of go through some of it. These criteria were developed through testing, both empirical and laboratory testing. These are the conditions that are required to stop or dramatically slow corrosion on steel. According to NACE, the IR-free or instant-off potential can't really be more negative than 1100 to 1150 millivolts. So a good reading for a tank would be between 850 and say 1050 or 1100 millivolts. The 100 millivolt polarization requires that you measure the formation and decay of that polarization. Alyeska historically was experiencing some issues with their CP systems on the tanks and the data collection. So in 2003, they hired a gentleman named Bob Gumow with Corange out of Toronto to assess their systems. Bob is probably the most referenced corrosion engineer in the world at this point. He's certainly the most referenced living corrosion engineer in the world. He's very highly respected and known throughout the industry. One of the findings he passed on was that the instant off readings that were more negative than 1350, he was giving a little bit more leeway than NACE, were just kinetically not probable. It couldn't happen. He also stated that readings that appeared to be good, that were associated with high readings, also had some of that inherent error in it. So just because if one reading is bad, it probably indicates that multiple readings have an interference, have an issue. This is, we got that out of the way. This is the data that Alyeska typically reports. Welcome to my world, by the way. And I'm going to go through it relatively quickly and explain. Column 1 and column 3 are just the location that the data was collected. Column 2 is the time that it was collected. Column 4 is the calculated shift of the polarization. So that's what you would measure against the 100 millivolt criteria. So when they say 0.332 volts, like in this reading right here, that's 332 millivolts. So this is what you would use to compare against the 100 millivolt criteria to determine if the structure is protected. Next column, column 5, is the on potential. It's not very useful data. It's good for troubleshooting, but not really for anything else. Instant off data is what you would use to compare against the 850 millivolt criteria. That's the IR free or instant off data. Column 7 is the date that the deep hole data was collected, and column 8 is the deep hole data. The 2016 to 2018 data, all of the 2016 to 2018 data that we were provided for tank 8 suggests that this tank was very well protected from corrosion when related to the 100 millivolt criteria. Everything met the 100 millivolt criteria. The lowest was 131 millivolts of polarization, and the highest was 585. We know the tank's actively corroding, so either there's something wrong with the criteria or there's something wrong potentially with the collection of the data. So we're going to look a little closer at that. There are several issues. First, this is the deep hole data. It was collected in 2015. The standard requires that you use the formation or the decay of polarization to determine whether you have 100 millivolts of shift. And typically what they do is they measure the deep hole, they subtract it from the instant off reading, and that gives them this number. In this case, 332, that should be great. But this was collected in 2015. This one was collected in 2017. The instant off data was collected 1, 2, and 3 years later. The deep hole readings change over time due to moisture content, due to temperature, due to soil chemistry, and actually the application of CP impacts the deep hole reading. So the fact that you have a CP system on will change this reading, which is why you have to collect it at essentially the same time as your instant off reading. Why the code or the standard requires you to measure that formation of decay. And that's not what's being done. This is a pulling out some of their instant off data. It's not terribly negative. It's more negative than what NACE suggests would be reasonable. It's negative enough that it should have thrown a flag to the operator to take a second look and dig into things a little bit more. I looked at the tank in the very same tank cell, tank 7. It's adjacent to tank 8. It's monitored by the same personnel using the same techniques and the same procedures, and they're reporting IR-free data of up to 2.7 volts. This is just an excerpt, and these are up in that neighborhood. These are voltages. These cannot be achieved. It's not physically possible to polarize steel to that level. So there's even, there's a novice error here. But as Bob Gamow noted, and as we agree, even in the areas where the error isn't as obvious, it's still undeniably an inherent part of that number. So it calls into question all of the data that's collected in this manner with these at this time and in this manner. And keep in mind that the IR-free data is what you subtract the deep hole data from to get the calculated shift. So if this data is bad, then the data you're using to compare against 100 millivolt is also in error. So these are well beyond what Bob Gamow and NACE and we agree could be normal. Alyeska obviously realizes that there's some errors in their data, and they've caveat the data with this note that readings that are more negative than 1.4 volts are due to being taken in close proximity to the mixed metal oxide grid. I don't, in my professional opinion, that reasoning is flawed, but you're interrupting a current. Any electrical field around that grid should collapse, and it shouldn't impact the reading. But regardless of what's causing the error, they're admitting here that there's an error with the data. What they're not picking up is that even if there's an obvious error in this data, there's an inherent error in all of the other data that's collected at the same time, because you've got an interference issue, you've got some other influence. To our knowledge, Alyeska is still collecting the data in the same way, the CP data, despite the conclusions that their consultant, Bob Gamow, provided them 17 years ago. These are inherent systematic errors in Alyeska CP data that leaves the operator with a false sense of security, believing their tank is protected, when in fact, like on tank 8, they're experiencing an elevated corrosion rate, despite what should in fact be a well-protected tank. I want to take a look at talk a little bit about their tank secondary containment systems. These are liners that run beneath the floor, under the sump, all the way up to the other wall. They're batten battered down. It should be tight. Alyeska has been experiencing water accumulation between some of their tanks for more than 30 years. However, there's other tanks that are not accumulating any water. None of the in-your plate extension ring wall seals have been maintained on any of the tanks. They're all subjected to 70 inches of rain a year. Some of them had subfloor drainage systems, and some of them, we don't know if they all do, but again, that alleviates some of it, but it doesn't alleviate it all. Those are located significantly above the elevation at the bottom of the sump. So brings to question is why some tanks are retaining water and some others aren't. And the only conclusion I can come to is that there's a fault in your secondary containment liner. I think in light of that, I think a more comprehensive assessment of the tank subfloor secondary containment is warranted. Alyeska has done some isolated looks of that in the 90s, but I don't believe, to my knowledge, they've comprehensively assessed those to see how tight they are. Kind of in summary, the tank 8 return to temporary service, I think the approach they took was pretty conservative. I think their corrosion rate they used was quite conservative. I think there's a very low risk that you're going to have a corrosion problem in the floor of that tank before it's removed from service in 2023 for a new floor and a new CP system. Regarding subfloor water accumulation, tanks that have competent secondary containment liners are going to retain water and have saturated soils at least up to whatever drainage system they have, or to the ring wall if they don't have a drainage system. Either way, there is some level of buoyant forces that are acting on that sump. It's negated when the tank is full and you've got the hydrostatic head of the oil pushing down. But when the tanks are empty, that's a risk. Regarding cathodic protection, Alyeska CP system is not being conducted in accordance with industry standards that are used worldwide. There are just inherent systematic errors with the data that they're reporting that leave the operator, regulators, and frankly, the general public with a false sense of security. You're led to believe that these systems are protecting the floor. And the fact of the matter is, we see with tank 8, it's actively corroding. They're not being operated effectively. Regarding tank secondary containment, the variation, the amount of water that's being retained beneath those tanks, and I think to some extent the wide variety and variation in the CP errors that we're seeing lend some credence to there being perforations in some of those liners. I think it warrants a closer look and a more comprehensive look. Our next steps, we're still pending data. We're awaiting the balance of the data that we requested from Alyeska in June of last year. Pending receipt, we will complete a final report. That'll include conclusions and recommendations going forward. Willing to take any questions anybody has.
Thanks, Bill. I guess you'd have to stop sharing your screen so we can see anybody that has their hand up.
Let me see if I can figure out how to do that. I'll let my IT guy leave.
That's going to be the little red stop share button that's kind of on the bottom of that window, that sharing window.
Hang on, I'm going to close every window I have. There I am.
Perfect. Thank you.
You got it.
You got it back?
All set. You bet.
Okay.
Thank you. So we do have a question from Jim Herbert. Go ahead, Jim.
Thank you, Bill. I must say I got lost a little bit in the electrical stuff. I changed light bulbs, but not much more. So, but I get the impression. But here, just a couple of things, and maybe you could clear up for me. Over the years, I assume when they deal with the exterior of the tank, they do a sand sweep or sand blast to get it down to bare metal and then epoxy coat.
Yeah, the shell of the tank is they've been spot blasting it every time they do a maintenance coat, and they'll sand blast it. They'll put a couple of coats of epoxy on. Then they brush blast the whole thing and they apply a urethane. Epoxies don't have good ultraviolet resistance. So if you just leave the epoxy, it'll chalk and disappear over a matter of years. So the urethane's got good UV resistance. So eventually those epoxies will get too brittle and they'll eventually have to strip the whole tanks. But so far they've been able to feather it into the existing coating and just top coat.
And so there's really, from your knowledge, virtually no wastage or on those shell platings. It's the floor that people need to concentrate their efforts on.
Yeah, the shell is coated 3 feet up on the inside, full length on the outside. They've seen very light thinning way up in the headspace, so above where the oil is coating it and covering it. They see slight thinning way up high, and they see some thinning on the roof plate. But for the most part, the floor plate has been the bugger. That's been where everybody's focused.
I think I was lucky enough to see them replacing the floor on one of the tanks up on the slope. And it's like 1 inch. Well, I think this is a quarter, but sometimes they use thicker plating on the floor.
Pretty rarely. Once in a while, an operator will bump it up and go to 3/8. And I think I heard a rumor that they might be doing that with this tank. But for the most part, almost all operators have 1/4 inch plate on the floor.
And so they lay big sheets down and then weld them in place and then ultimately paint the top.
Correct.
So of course, if you painted the bottom side, you'd burn off some of that paint when you went to weld, but wouldn't it make sense to try to get some sort of protection on the underside before you weld? Or is that, it's just bare metal the way it works, huh?
Yeah, it's bare metal. That was discussed a few times. I don't remember exactly why it was walked away from. You would have to strip it off or leave it bare, you know, probably 6 inches on either side of the edge of the plate. They're lapped plates, so they overlap some. I don't know if it was walked away from for cost or the practicality of it. You'd still have issues at the weld lanes, at the bare areas at the edge of the plate. So it wouldn't totally alleviate it. It might help. It would certainly reduce the capacity that your CP system needs to have, but because you got much less bare area. But I'm not sure it would help the overall. You know, when we're working with these tanks, we're working with the worst case. We're looking for the deepest pit and the highest corrosion rate, and I'm not sure it would help us with that. It might, but the one benefit, you would be able to go away with a smaller CP system. You wouldn't need quite as much amperage.
Okay, yeah, obviously I'm the novice here. I'm just kind
No
of
worries.
trying to learn, and you know what's cooking. And similar with this question, since water underneath the floor between that and the secondary barrier there is a problem, why isn't there some kind of way to facilitate drainage out of that area? You know, you could drain or even suck water out so you wouldn't have that distortion of the sump.
They have drainage systems that they've installed. Those are located kind of at the perimeter of the tank. They're up pretty high though. They're a couple feet higher than the bottom of the sump at least, and probably more. So they don't alleviate that risk altogether. You know, some of the tanks may have CP monitoring tubes that are located relatively close to the sump, which would help you. You could use those to pull moisture out. Tank 8 doesn't. Tank 8's monitoring tube goes straight across and doesn't get near the sump. So I don't know that it wasn't recognized as a problem. If you have competent secondary containment and you sealed the annual plate extension to a ring wall, you wouldn't have that problem with moisture migrating underneath. Most operators maintain that seal.
Mm-hmm. And one final question. When they do replace the floor in these tanks, do they also put in a brand new secondary containment liner? We've had issues or worries, and Austin has researched it, where the catalytically blown asphalt that's within the dike has had difficulty. Is this the exact same thing under the tanks, or have they upgraded it to some of the more modern ones?
They typically don't excavate deep enough to get to the secondary containment liner. They typically leave some layer of soil between the secondary containment liner and where they put a geofabric down and install new gravel in the CP system. So they haven't been, to my knowledge, none of the ones I was involved with, they haven't been replacing the secondary containment liner. They've repaired it where they've hit it. I know they did some of that, but I don't believe they've been replacing it.
And to the best of your knowledge, then those are the originals from back in the 70s?
Correct.
That's a long time.
All right,
thanks so much. Appreciate your feedback.
Robert Beadle.
Yeah, good afternoon. Good presentation. Just to help my understanding, I feel like Jim there, I'm a little bit of a novice on some of this here. I do have a boat, and I found out that an aluminum anode was better than a zinc for controlling electrolysis on my boat. But I'm kind of it's a sacrificial anode.
Right.
So I'm not totally sure how this cathodic protection works on these tanks. Are they just interrupting the electric flow, or how? I mean,
It basically, they use impressed current, so the anode material itself doesn't disintegrate. With your system on your boat, you have to replace your anodes periodically because they dissolve. They sacrifice quicker, they corrode quicker than they would if they were not connected to anything, because they're sacrificing themselves to protect.
Less noble.
Correct. They're sacrificing themselves to protect your boat. With the tanks in most systems in an industrial setting, they're using impressed current. So they use an anode that's noble and they drive electrons off of that. What you're doing with your boat is a battery. Bottom line, a sacrificial CP system is just a battery. What Alyeska uses, what most industrial owners use is an impressed current system. So it does the same thing. It's just using a noble anode to drive current to the steel surface. Those extra electrons actually shift the pH of the steel and drive it to a place where it's more inert. Does that answer your question?
It sounds like we should have a beer and
Yeah, there you go.
understanding.
A beer and a napkin, I could probably get you straightened out.
So is there anything, with this system, there's nothing actually sacrificial. It's just that with the current, they negate the electrolysis action.
Right. They have a rectifier that takes the place of yours is a battery. The zinc is a battery, or the aluminum, if you've got a steel boat, is a battery. This system uses an impressed current. It uses a rectifier to drive that current. Same exact, same science, same principle. It's just a different power source.
Oh, okay. Okay. That's interesting to me. Just wish I could do something like that on the boat.
Oh, you can. It's just more expensive.
But less time. But anyway, thank you so much.
You bet.
Any other questions? Wayne Donaldson.
You may have, excuse me. You may have covered this, but I think I heard you say that the tank was going to be re-inspected or worked on in 2023. Is that right?
Correct. Their plan is to take it back out of service, remove the floor, and replace the CP system in the floor in 2023.
Replace the C. So what does that involve? The whole CP system being replaced? Is that beneath the floor?
Yeah, correct. And they have they mount sacrificial CP anodes in the tank, adjacent to the columns, just in case there's any coating holidays. But the systems we're talking about are the bottom side, and they're impressed current.
Will that solve the issue as far as you're concerned?
If they do it correctly, it may not solve the monitoring issue. The monitoring issue is not, I've seen it on piping. I've seen it on the main line. It's not a there may be problems with that system, but the monitoring issue is independent of the system. It's not going to fix.
The monitoring issue was the readings that were incorrect.
The measurements are taken are incorrect, and that's independent of what kind of system you have. I've seen similar data on the piping in Valdez and on the main line.
And so you have recommendations that could be passed to Alyeska for improving that?
Well, I do. They simply need to follow the requirements of the standard. NACE is pretty prescriptive in their standards as to how to go about monitoring these systems, and they're not following them.
Okay, so my other question maybe for Donna is that that would be a DEC oversight regarding these measurements. That would be something DEC would be monitoring, or should
I believe
monitor?
the requirements are DEC in terms of following all of the API standards and that sort of thing. We have Roger Burley on the line that could probably confirm that, but yes, my understanding is it would be DEC oversight.
And this is one tank out of how many tanks are on site there? That 14, 16 tanks on site?
There's 14 crude tanks. There's 2 ballast water tanks. There's, I don't know, I'm winging it a little bit here. There may be 5 or 6 other, there's at least 2 fuel tanks that have CP. There may be others.
And this was the only tank that you looked at?
this is the only tank I looked at in this study. I did look at some of the tank 7 data. Just to add, tanks 1 and 3 are regulated by PHMSA, as well as some of the piping on the terminals is actually regulated by PHMSA and not necessarily ADEC.
Okay, well, thank you for your work. It sounds like we have some good recommendations that we're going to have to work with in the future. Thank you.
You bet.
Thanks, Wayne. Mako Haggerty?
Yeah, this is probably a little, I'm not sure who can answer this question, but it was a question I had earlier, actually. The capacity for storage, we lost that last spring when we kind of had a glut and the demand of oil was way down. How much capacity did Alyeska have during that time, or were they completely full? And I don't know if anybody here has that answer, but anyway, that's my question.
Robert, I can answer that question. Actually, Mako, if you go to section 5-1 of your board notebook, there's a table in there that we put in there that shows you the capacity of the terminal. And during that, you'll see the trend during that time period. So if you go and look at that graph there, Mako, just off the top of my head, I don't recall it getting into the 90% capacity or anything like that, but you can go see that data from this spring in your board notebook.
Thanks for that, Austin. So Bill, you say that they lap that plate. How much of an overlap is there when they weld that? And I suspect they only weld it on the top side for sure.
Correct. It's the annual plate, so the stuff around the edges is butt welded. It's thicker. I want to say it's in the neighborhood of 1 to 1.1 inches. But then that only runs in 6 or 8 feet into the tank. Then they've got 1/4-inch floor plate that laps up onto that. And yeah, they only weld it on the top. They only have access to the top, so it's only welded on the top. It overlaps probably 2 to 4 inches, something like that.
So that would catch moisture if that water's pressed up into the bottom of that and create more of an issue.
It would certainly be a crevice that could collect moisture.
Have you ever seen a column lift the roof a little bit, deform the roof if say near the sump is floating a little?
No, when I did see a sump floating, it actually bent the column footing and indented the floor a little bit. It didn't look like it significantly lifted the column.
Gotcha.
I have seen on other tanks columns floating in the air where they haven't been supporting anything, but yeah, not in Alyeska's tanks and not on this one.
And I must say, I've taken a course in impressed current CP systems, and it took certainly more than the 10 minutes you tried to cram that some understanding into. So, Linda Swiss, you have a question?
Yes, I just got a couple questions. You didn't mention, or I didn't catch that you mentioned that column had penetrated the floor in tank 8. So I assume, I mean, is that a big concern? I mean, that was obviously repaired, but is that part of this big concern with this tank?
I think there was one column that they had forgot to remove a nut. When they work on these tanks, they jack the columns and they typically install big nuts underneath them to keep it off the ground so that they can inspect underneath them and coat. And my understanding is, I want to say it was column 43, they neglected to remove the nut and they actually indented into the floor. They put a checklist together that I think multiple people have to go and peek underneath every column before they put it back in service to ensure that they don't have a nut under it anymore. Yeah, probably shouldn't have happened to start with, but I think with the checklist, that pretty well keeps you from allowing that to happen again.
And then my other question was about that sort of grout material around the annular ring. I wonder why they wouldn't have maintained that over the years. I don't know if I was aware that a material like that was ever used in that interface right there.
Yeah, that practice was stopped before I came on board in like 1990.
Mm-hmm.
You know, the tank is not actually, it's not tied to the foundation at all. It rests on it.
Mhm.
So, and that steel expands and contracts with temperature more than the concrete will. So it's a difficult seam. It's a difficult seam to maintain. It's a difficult seal to maintain.
Mhm.
But most people do. Like I said, they stopped maintaining it back before I came on board. We worked with Alyeska's coating contractor to propose an alternative, which would have lapped up on the side of the tank and down over the annular ring of the ring wall to keep that from happening. They were concerned that would cover up their chine weld, which is a valid concern, and they wouldn't be able to inspect it. And that's kind of a critical weld to keep an eye on. So it never really went anywhere. But no, they had, to my knowledge, they haven't been maintained since sometime in the 80s.
Okay, thank you.
You bet.
Thanks, Bill. Is there any more questions? Oh, Robert Beadle.
I'll be quick. Bill, you know, to cover that gap, I mean, it wouldn't have to be structural. I mean, we do it on houses all the time, you know, and it could be up a valid amount, you know, a foot to, but when you're talking about rain water coming, not so much blowing, I mean, it seems like a simple fix to me.
Yeah, it's not structural. All it is it's usually a flexible sealant like you use in your bathroom, and maybe an industrial grade of it, but it allows a little bit of movement, but it needs to be maintained. It's not, you know, it's not going to last forever.
Sorry, Bill, I was talking about the, you know, like an awning or something on the perimeter of it. You know, that you're talking about rainwater running off the top of the tank and then training in, and, you know, I mean.
Yeah, anything you put on there kind of has to be structural by nature. A lot of snow, you know, a lot of snow slides off those tanks. So anything at the base has to be pretty stout to withstand that. So if you hung up any kind of a lightweight material to shed water off there, it would get stripped out the first time the snow shed off the roof.
All right. Well, thanks, Bill. Thanks, Austin. We looks like we have a better understanding of what's going on there. So hopefully the cathodic protection readings is not a systemic problem, and it's something that will be resolved. So thanks so much.
You bet. If I can answer any questions, by all means, drop me a note.
Good enough.
Take
Thanks.
care. You bet. Bye.